Feel free to start anytime.
Okay, can you hear me?
Very well.
Good. So I've been asked to give a short overview of the US neutrino program, um, moving from short to long baselines. And I'll start with the short baseline program at Fermilab with this bird's eye view of the uh, short baseline program uh, at the lab. Uh, the beam coming from the left, you see the three liquid argon detectors that form the short baseline program, which is SBND, uh, closest to the beam source, then Microboon, and then Icarus. And there also you see the like a Celtic burial mound, or so this is the mini boon experiment that has previously taken data. What these experiments of the short baseline program have in common is the liquid argon technology. So a short introduction here, which of course is also then relevant for the part of my presentation that is on Dune. So the idea of liquid argon TPCs is that you have a neutrino interaction producing charged particles that ionize the argon. Then under a strong electric field, they drift towards, in this case, wires. It can also be pixels or other things that record the charge. And through that, you get, at the end, either two-dimensional or three-dimensional reconstruction of the event. In addition, you also read out scintillation light, which is much faster than the drifting charge and provides crucial timing and also spatial information. Microboon is the oldest experiment in the short baseline program and has been taking data for 5 years and ended data taking in 2020 as about 5 years ago. Microboon is special as it is really exposed not only to the one neutrino beam, but two neutrino beams, as you can see here, both the boosted neutrino beam and the NUMI beam. And in a moment, I'll show you why this is actually quite important. One of the main aims of Microboon was to just demonstrate that this technology, the LAR-TPC technology, can be run stably and also produce a science result. And Microboon has succeeded in that, publishing, well, up to close to 100 papers now, 85 papers, and of course also graduating a lot of PhD students. You see here, and I'll show a few more of these in an event display that just shows the power, the imaging power of the liquid argon technology, which liquid argon obviously is not blue, but this is the color used here in the event display, and then you see particles emerging from them, and the color coding gives us the specific energy loss. The SBND detector has now started taking data for about 2 years. It is about 100 tons of argon, again a TPC, which is shown here as it is being assembled with a typical design of the TPCs, modern TPCs, which we see with a cryostat, and then the TPC going into the cryostat and having both readout for charge, in this case with wires, and for light with photomultipliers. It also has a cosmic ray tagger because these detectors are on the surface, which means there's a significant rate of cosmic rays. And because liquid argon TPCs are relatively slow, they integrate over quite a few cosmic rays crossing the detector. As Microboon and all these experiments, these are international endeavors with, in this case, 40 institutions from 5 countries. Just showing here the strength of the performance of and the success of the SBND detector. so running over the last 2 years. Shown here is I don't know whether you can see the cursor, but you see the electron lifetime, which is a very important parameter which defines basically how long the drift is, and it's very stable and over the period of data taking. Down here, the signal over noise, so there's an excellent signal over noise performance. The integrated data measured in protons on target, and down here, the DEDX plot as a function of the residual range, which shows that for muons and protons, there is already an excellent calibration of the data. Again, a few event displays of muon neutrino or electron neutrino charge current candidates, where you see the neutrino coming from the left. Well, you don't see the neutrino, but then you see the interaction and as I said before, excellent imaging capability of these type of detectors. Finally, there's Icarus, the far detector of the SBN program, which is significantly larger, about a factor of 4 larger. Again, 2 TPCs in 2 modules with light and charge readout. Icarus has been operating also for several years now and collected a lot of data, which also covers BNB and NUMI, similar to microboon, but not quite at the same relative rate. So why is this 2-beam exposure of microboon really important? And I would like to highlight here a result which was published just a couple of weeks ago in Nature, which is the search for sterile neutrinos and a study of the low energy excess, which is, of course, one of the primary and has been one of the primary science goals of microboon and generally the short baseline program. What you see on these plots is on the x-axis a mixing angle, and on the y-axis the delta m squared between the first mass eigenstate and the fourth one, which would be a sterile neutrino. Sterile neutrino because it's not been seen in Z boson decays. The typical mass scale for this is about an electron volt, which is relatively large for neutrinos, and that's driven by the baseline of the experiment and the oscillations you would see if oscillations occurred into these sterile states. The exposure to both beams allows to resolve degeneracy, significantly increasing the sensitivity of the experiment, which now covers a lot of the range, or the entire range of several of the anomalies which have been reported over the last 20 years by LSND, mini-boon, but also the gallium and neutrino 4 anomalies. And you see that this microboon result now basically excludes the simplest model, which is a 3+1 model where there's one extra sterile neutrino as an explanation for these effects. Another very important science goal of the short baseline program is to measure neutrino argon cross sections. First, because they're interested in its own right, and but also in preparation for Dune. And I'm not going to cover all these plots here, but it shows these are all publications from microboon, that there's a wide range of measurements that tests various models. Another important physics topic is the search for beyond the standard model. Usually this is for lighter particles because it is a lower energy beam that's compared to what you would see at a collider, but usually because we are here at the intensity frontier also with small couplings, and you see it on these type of plots where usually the coupling is shown or the mixing on the y-axis and the mass on the on the x-axis. And these are searches which have been performed for heavy neutral leptons, Higgs boson scalar, or dark matter particles in so-called trident interactions. And in all these cases, the experiments are world-leading in terms of sensitivity. SBND is the closest experiment to the source, the target, and that means it will have a huge number of neutrino interactions. And what you see here in the middle plot is I lost my cursor. In the middle plot is just 3 days of data for a new mu charge current data set, and it just shows what can be achieved with a full data set. It's particularly interesting because the energy range, and that's shown here, of the beam overlaps with the dune energy range in the peak. So this is a region which is particularly important, and we have said already so in Marcel's talk that the understanding the nuclear interactions of neutrinos is critical for the science program in neutrino interactions. A nice additional aspect of SBND is that it's actually able to use the prism concept, which some of you might have heard about, which is basically where you, in Dune later, you would be moving the detector sideways, or in T2Ks upwards, to probe different parts of the beam. You don't have to move the SBND detector. You can actually do this within a single detector because it is so close to the source. The SBN program, where here I define SBN now as SBND and Icarus, that are running concurrently, will be able to also, of course, reach even better sensitivity to the sterile neutrino parameter plane, which is shown here. And you see that the Icarus and SBND analysis jointly together, where one is the near and one of the far detector, exclude significant new ranges of parameter. The Fermilab neutrino program is we're moving here from short baseline to long baselines. And there is the NOVA experiment, which also where the beam originates at Fermilab, but then goes over a baseline of 810 kilometers, the longest baseline of an operating experiment, to the detector in Minnesota. And it's not a liquid argon technology. It uses scintillator technology, and it started data taking more than 10 years ago and will probably end either this year or early next year. NOVA has done a lot of different measurements. I'll focus on what is relevant, particularly also for in preparation for Dune, is sensitivity to mass ordering and CP. And what you see here is the red and the blue curves are the posterior density that interprets the data both in terms of a normal mass ordering blue and inverted mass ordering red, using different constraints from Daya-Bay. You see that there is some favoring of the normal mass ordering in this particular case. If you now either assume normal or inverted mass ordering, you can also look at delta CP, which is at the bottom right. And for the normal mass ordering, you get the blue curve. For the inverted mass ordering, you get the red curve. And you see that for normal mass ordering, the data prefers small delta CP, whereas for inverted ordering, maximal CP violation is preferred, and the full range is not in the 3 sigma allowed interval. If you compare this with the other operating long baseline experiment, T2K in Japan, you get an interesting set of plots here expressed as sine squared theta 2,3 versus the CP violating phase. Left is the normal mass ordering, and in right the inverted mass ordering. And the bottom line is, if you look at inverted mass ordering, that experiments seem consistent. In the normal mass ordering, they are not, and favor different delta CP ranges. Within, still, this is only a few sigma. This has also been studied in a joint fit by Nova and T2K that's been published also in 2025 recently in Nature. And of course, it's always a bit difficult to combine experiments, even though the significances are not that high at this level, that aren't really consistent. But you see that depending on different assumptions, both normal and inverted mass ordering are still possible. That brings us to DUNE, which is, as we all know, the flagship long baseline neutrino oscillation experiment for the future coming decades. It has 4 key ingredients: a high-power wideband neutrino beam, the far detector, which has a long baseline of about 1,300 kilometers. This is relevant because it actually allows for matter effects to happen. The liquid argon technology, which provides excellent flavor and topology reconstruction and energy reconstruction, and a movable, high-capable near detector. And movable here means, as I said, it can actually probe different distribution and different parts of the original neutrino beam. Why is this important? Because for different oscillation parameters, the original spectrum is modulated in different ways, and therefore we have to reconstruct the energies very well. We have to know the original beam properties very well and the energy distribution, and the long baseline and the mass effects allow us to resolve degeneracies between mass ordering effects and delta CP. DUNE is a global collaboration, as we see here, with I don't even know, like 30 countries currently. And it's envisaged in 2 phases, phase 1 and phase 2. Phase 1 is 2 far detector modules in South Dakota, where phase 2 would then add modules number 3 and 4. Phase 1 for the near detector is a liquid argon TPC using pixels, the TMS, and both would spectrometer, both together would move sideways with the prism concept, and then the on-axis sand detector, which is based on the Chloe detector from Frascati. The beam, the original beam, is envisaged to be 1 megawatt approximately, and then increasing to 2 megawatts. For phase 2, I said that 2 more modules would be added. For near detector, the plan is to replace the TMS by a gas argon TPC, which would allow to measure neutrino interactions with very high precision. The success of DUNE's program was only possible through the prototyping work which happened at CERN, and Gina already showed that yesterday. This is the CERN neutrino platform and an 8 by 8 by cubic meter cryostat, which will look like is 1/20th of the DUNE cryostat. And there the technology has really been demonstrated at scale. And I just show a few pictures. This is inside ProtoDune. I like to show it because it's beautiful. It's not gold, it's just the light to protect the light system. I always find it amazing that, if you come from collider physics, that the center of the detector is actually empty. Well, there's liquid argon in it, but it's quite different from a collider detector. This is more pictures from ProtoDune, and this is a screenshot from a video which you can find online, which shows how the liquid argon is added to the detector. You see the big anode planes here. Beautiful. So again, this technology is fantastic in terms of imaging, and this is a real data event from ProtoDune, pi plus going stopped in the detector, creating a proton, and then there's a pi 0. And Well, this gives us the confidence that we can actually build the detectors, and the timeline for phase one is shown here. And we are now in 2025, where the caverns have been excavated, are being outfitted, and pretty soon we'll start constructing and filling the far detectors, and then in parallel also work on the near detectors. I have had the privilege to be down in the mine a few weeks ago. I was actually me standing there. It's quite impressive to see the cavern now being fully excavated and available. And the cryostat construction is starting soon. The parts have been delivered, and then will be followed by the installation of the first two modules, the vertical drift and the horizontal drift. The Dune near detector, as I said, is a crucial part of the setup, and without it, you can't do the physics. The DOE this year has removed the cost cap set by CD1RR, which provides a clear path for us and for the US project to deliver the fully qualified detectors for Dune phase one, which is crucial. There are challenges related to the near-site civil construction at Fermilab, and both the US project and the Dune collaboration are jointly exploring currently different options to address these issues to be able to accelerate the construction as much as possible. In parallel, there is prototyping for the near detector going on. This is just an example of the ldner detector, which has its second run started like a month ago or 2 months ago. It's a pixel detector, and a lot of this has also been happening in Switzerland at the University of Bern, where you see one of those modules. Why pixels and why modular? Well, the reason is that we are actually now in the high occupancy regime for neutrino detectors, and this is the simulation of a beam spill as it would be seen in the detector. And so this is a new challenge. It's also a challenge for the reconstruction and software, which I cannot talk about here due to time. But the two things which address this for the near detector is the pixelation and the modularity. So let me talk in the last couple of minutes a little more about the physics highlights. The first and early Dune physics highlight is the mass ordering. What is particularly important here and visible is that first, once a detector turns on, due to its unique capabilities, it can determine the mass ordering very, very quickly for a wide range of underlying parameters. And you see this sensitivity here for an assumed starting date in 2031, where the 5 sigma can be reached in months. Ultimately, Dune is a precision experiment, and you see on the right the contours for different assumptions of the exposure of the experiment and how that precision improves for a variety of parameters and the mixing parameters. On the left, you see the phase or the sensitivity to the phase as a function of years, and it shows in the staging approach how this increases when you add a third and fourth detector, and also the more capable near detector, which is the gas argon, including the gas argon TPC. And at each of these, you reach steps going forward. And of course, another important step is an increase in beam power. The ultimate goal is precision physics and precision measurements. And here you see the resolution on delta CP, and as a function of exposure and as a function of the parameter itself. And this is really the ultimate strength of this experiment, that it will be able to constrain this and other parameters with high precision. I've talked about accelerator-based neutrino physics, but there is a whole physics program for non-accelerator-based neutrinos, which I haven't really had the opportunity or time to talk about. Let me just quickly mention supernova, and there's also solar neutrino physics, where DUNE is complementary to other detectors like Super K and Juno by being sensitive to the nu spectrum. A signal, this is shown here, is a 10 kiloparsec supernova burst. Within seconds, we would see this burst and be able to actually determine the mass ordering just from this one single event. It's a challenge for the detector because the neutrinos are totally different energies, whereas we talk about GeV for accelerator-based neutrinos, creating meter-long tracks in the TPC. These are low-energy nuclear energy range neutrinos, which means they are just a few centimeters long. So this will be quite a challenge for the detectors. The path towards phase 2 of DUNE, which will be critical for being able to do the full physics program, is now laid out. We published a white paper in JINST a few months ago. There's the P5 recommendation, which mentions clearly the importance for a re-envisioned second phase of DUNE with a third detector and a fourth detector, an R&D for that. And we just submitted an LOI for ProtoDUNE 3 run, we as DUNE, at CERN, which will test some of the technologies for a fourth module, which sometimes is called the module of opportunity, as it will hopefully also be able, in addition to doing DUNE physics, expand its physics scope, for example, to lower energies. The European strategy is ongoing, and I just would like to highlight here the recommendation by the strategy group, which came out 2 days ago, and which clearly supports LBNF DUNE and recognizes the importance of the neutrino science program within the field. And the process is still ongoing, but I am confident, and I think we all hope for a positive recommendation at the end of the European strategy. So just quickly, I won't read all of this. The US neutrino program covers both short and long baseline physics. The short baseline program has been very successful, both in terms of liquid argon technology and physics program. There's an ongoing long baseline program with NOVA, which provides really intriguing hints in terms of CP and mass ordering in the neutrino sector. DUNE is designed to test the three-flavor paradigm. Assuming that is correct, will provide extremely precise measurements of its parameters and breaking degenerates this because of the setup. The DUNE will also be able to determine the mass ordering basically instantly for a very wide range of parameters. The key ingredients are wideband beam, long baseline, liquid argon technology, and the movable near detector. These are the things that make this experiment unique. Thank you.
Thank you very much, Stefan. There are a few questions for you in the live document from Heidi. Any comment on the effect of the new Juno results on the combined T2K NOVA fits?
I haven't seen. I'm not on T2K or NOVA, but so perhaps somebody else can make a comment on this. But it's of course a very impressive result, and I hope and assume there will be combinations. But if there is, Tricia, I see Tricia probably wants to answer this.
Okay,
Was I able to unmute?
Yeah, yes.
So the recent Juno result was reporting on the solar parameters. In order to do the combination between reactor and long baseline to get the mass ordering, they need to report on delta M squared 3.2 or 3.1, whichever one.
And then there's a question from Mike Albro. Can these liquid argon detectors make useful contributions to cosmic ray physics?
Yeah, there are measurements that we can do, and there are people who are working on this. The problem is, of course, that the liquid argon detectors are, especially the ones in the short baseline program that are running, are relatively small. So while you see you can measure the cosmic rays very well. Yeah, the volume is relatively small, and I did some studies actually a couple of years ago that show that at least for the short baseline detectors, the impact is relatively limited. But the problem in the far detectors is, of course, that they are a mile underground, so the rate will be lower. But I know there are some studies ongoing that could, for example, perhaps could measure some rates which might be of interest. Yeah.
Thank you very much, Stefan, for your very comprehensive talk.